Okay, so we're going to look at the type 2 kind of improper integral. Again, there's two types. There's the type where you have an infinite interval, and that's the one that we're looking at here in before. You know, when basically when one of the bounds is either infinity or negative infinity, you have an infinite interval. And then the type 2 kind is when there's an infinite discontinuity. Okay, so that's what we're going to be focusing on here now. As definition, it says that let f be a continuous function on the interval a to b, a is included, with an infinite discontinuity at b. Okay, so there's a vertical asymptote at b. Then the integral going from a to b of f of x dx is the limit as, now let's see, I'm approaching b from the left. If I'm going a to b, okay, I'm approaching b from the left, and so it'd be the limit as t approaches b from the left of the integral of going from a to t of f of x dx. Okay, let's see, now in this one, so let f be continuous on the interval a to b, where b is included, with an infinite discontinuity at a. Then the integral going from a to b of f of x dx is the limit as t approaches a from the right. So here's an example. You're approaching 1 from the right of the integral going from t to b of f of x dx. And then in item 3, suppose that you have a function that's continuous on the interval a to b with an infinite discontinuity at c, where c is some number between a and b. Okay, then the integral going from a to b of f of x dx is the integral going from a to c of f of x dx plus the integral going from c to b of f of x dx. So in other words, you're gonna cut the integral at c wherever there's the discontinuity, and that's going to be your bounds on these two integrals here. So we'll look at an example of that. All right, so here's one example. So suppose that we want to integrate going from 1 to 9 the function 1 divided by the cubed root of x minus 1 dx. Okay, well, so here's a graph of that curve. I'm going from 1 to 9. And now 1 is not in the domain, right? I can't divide by 0. So I'll have a vertical asymptote on the graph at x equals 1. Okay? The curve is going to go up, and it's never going to get to x equals 1. Okay? Now that's an infinite, that's an infinite discontinuity. So the integral is going to be thought of as a limit definition. Okay? Whenever you have these improper integrals, you'll always compute the integral as a limit. That will always happen, no matter what type you've got there. So let's see, I'm going to go from, I have the limit as t approaches 1, unless I'm approaching 1 from the right, of the integral going from t to 9 of 1 divided by the cube root of x minus 1 dx. Okay, so I use this definition here, condition 2, on that. And now we got to integrate this function. So that's by u substitution. So if I let u be x minus 1, du is dx, okay, and I got 1 over the cube root of u du. Now if x is 9, 9 minus 1 is 8, is the upper bound. And now, here's the thing. So 0 is the problem now on this new integral. Do not be the person that writes t minus 1 as this lower bound, because negative 1 is not a problem. Negative 1 is not a problem. Is 0, you can't plug in 0 here, okay? So you're going to be approaching 0 from the same side. It's always going to be approaching from the same side. And the lower bound here is going to be just plain old t. Okay? And so then we have the limit as t approaches 0 from the right And by the way, the direction is important. Okay, you don't want to just say limit as t approaches 0 and then keep it as that. You always have to indicate from the right or from the left. Okay, you're approaching from the right side here. We don't have any graph on the left side that we're looking at. And the antiderivative would be the antiderivative of u to the negative 1/3 is u to the 2/3 divided by 2/3. Flip that, so it'd be times 3/2. And I'm going from t to 8. Okay, and I can plug in my bounds now. So when I plug in 8, let's see, 8 to the 2/3 power. Well, 8 to the 1/3 power, or the cubed root of 8, that'd be 2. 2 squared is 4. 4 divided by 2 is 2, and 2 times 3 is 6. Okay? And then minus, when I plug in t, I got a minus 3/2 t to the 2/3 power. I'm approaching 0 from the right. So at this point, now I can just plug in my bound, and I get 6 minus 0 is 6. Okay, so this infinite region here actually has a finite area of 6. Okay, and so that would be an example of a convergent integral. Here's another problem. So what if we were going to integrate on the interval 1 to 4, 1 divided by x minus 2 dx? Okay, well, 2 is a problem. Okay, and 2 is between 1 and 4. So I'm going to cut this integral into two integrals at 2. Okay, and because there's a discontinuity at x equals 2. So we're going to go from 1 to 2. We're integrating 1 divided by x minus 2 dx. Okay, and then plus the rest of the way, we'll go from 2 to 4 of 1 divided by x minus 2 dx. Okay. Now, let's see. So the first integral is an improper integral. So because I can't plug in 2 there. Let's see. I'm going to use the limit definition. I got the limit as v approaches 2 from the left. If I'm going from 1 over to 2, I'm approaching 2 from the left side. And I'm going to go from 1 to v. We're integrating 1 divided by x minus 2 dx. Okay, plus the limit as w approaches 2 from the right. Let's see if I'm going from 4 over to 2. I'm approaching 2 from the right side. Okay, so, and I'm integrating going from w to 4, 1 divided by x minus 2 dx. Okay, and now with these two antiderivatives, let's see, the first one I got the limit as v approaches 2 from the left of the ln of the absolute value of x minus 2 going from 1 to v. Don't forget about the absolute value bars there. And then plus the limit as w approaches 2 from the right of the ln of the absolute value of x minus 2 going from w to 4. Okay. Again, don't forget about the directions there. You get the left side and the right side. Okay. So then the next thing is I'm going to plug in the bounds. So when I plug in v, I get the ln of the absolute value of v minus 2 minus the ln of the absolute value of 1 minus 2 is negative 1. The ln of the absolute value of negative 1 is 1. So the ln of 1, that's 0, right? Okay, and then plus the limit as w approaches 2 from the right, the ln of the absolute value of 4 minus 2 is 2, okay, minus the ln of the absolute value of w minus 2. Okay, so then now if we were to look at a graph of y equals the ln of the absolute value of x minus 2, here it is right here. Okay, I got a vertical asymptote at 2. So let's see, if I'm approaching 2 from the left side, the y values are getting very large, but in the negative direction. So negative infinity would be the value of that limit. Okay? Plus, the limit of a constant is always the constant. And then minus the limit as w approaches 2 from the right of the ln of the absolute value of w minus 2. Well, if I'm on the right side of 2, then the y values are also going to be getting very large, but in the negative direction. So negative infinity would be that limit, and I'm subtracting negative infinity. So that really means I'm adding infinity to the ln of 2. The ln of 2 is just a number. So I get infinity as the overall value of this limit. Okay, negative infinity plus infinity. Now don't be the person that writes 0, because infinity is not a number. Infinity is just a symbol that we use to indicate unboundedness in the positive direction. Don't think of that as a number. Okay, there's nothing more that we can do with this item here, and we didn't get a number, right? And so the answer would be that this is a divergent integral. Okay, so the area is going to be some infinite region, in other words. Okay, and I got a caution statement here. Using this integral going from 1 to 4 of 1 over x minus 2 dx. So if I were to integrate that directly, I get the ln of the absolute value of x minus 2 going from 1 to 4. And then when I plug in the bounds, the ln of 4 minus 2 is the ln of 2 minus the ln of the absolute value of 1 minus 2 is 1. The ln of 1 is 0, so I get the ln of 2 as the answer. Well, that's wrong. Okay, and the reason why it's wrong is because so this is an improper integral. 2 is a problem. Okay, and we're integrating on an interval that includes 2. So we must do the problem as a limit. Okay, that has to happen. Otherwise we get the wrong answer. Okay, so I've got this note here. Because the limit is improper, we must be calculating it in terms of limits. Okay, that's important. So I'll see, sometimes on people's papers, where they will just they'll do the integral calculation without any limits, any limit notation. That's wrong. Okay, you'll get points off for that. Okay, so every improper integral has to be thought of as the limit definition. Use the limit notation for that. Okay. All right. Why don't you try? Here's another one. So what if I'm integrating on the interval of 0 to 1, x divided by the square root of 1 minus x squared dx? Okay, well, 1 is a problem. I can't plug in 1, right, because I can't divide by 0. So this is an improper integral. I got a vertical asymptote at x equals 1. Now, if I'm going from 0 over to 1, I'd be approaching 1 from the left side. And I'm going to say the limit as t approaches 1 from the left of the integral going from 0 to t of x divided by the square root of 1 minus x squared dx. And we can use a u substitution on that. So if we let u be 1 minus x squared, du is negative 2x dx. I've got an x dx in the numerator here, so I'll be able to knock out that part. A negative 1/2 will come outside of my new integral. Also, that's a constant. Constants can come out of limits as well. And so I'll replace the x dx part with negative 1/2 du. Okay? So the negative 1/2 is a constant that can come out of the integral and the limit. And I'll be integrating 1 divided by the square root of u du. Okay, now this is an improper integral, so everything about my new integral has to be in terms of the new variable, u. Okay, never ever mix and match u and x. That's bad, and that will get you a wrong answer. Okay, so let's see. If the lower bound is 0, 1 minus 0 is 1. Okay, now the upper bound is going to be t. I do not want to write 1 minus t squared. Okay, 0 is the problem. 0 is the problem here. Okay, so I'm going to be approaching 0 from the same side. be approaching 0 from the left side, and I want the upper bound to be just plain old t. Okay. By the way, with some of these problems, like you're going to have a u substitution in them. Okay, and you'll always replace the variable part with t. Just in general. Okay. So, and most of the time, when you make a substitution, like you're going to be approaching 0. We saw that earlier here. Where we at? So like in this problem here, I'm approaching 0. That will usually happen. Okay. And now this integral does not make sense in terms of the bounds. I'm approaching 0. So I'm going to go from 1 to 0? No, the lower bound is always the smaller number, okay? The upper bound is always the bigger number. So the next thing I do here is I flip the two bounds. I'm going to go from t to 1, and I throw a negative sign in front of the integral. I've already got a negative 1/2 there in front. So it'll be 1/2 times the limit as t approaches 0 from the left of the integral going from t to 1 of 1 divided by the square root of u, that's the same as u to the negative 1/2 du. Okay, and then I can integrate this function. So it's going to be u to the 1/2 divided by 1/2 is times 2. The 2 would cancel out with this 1/2 that's already in front of the limit. Okay, so those are gone. And now when I plug in my bounds, plug in 1 to any power is 1, minus t to the 1/2. Okay, I'm approaching 0 from the left. So, well, now there's no issues with plugging in 0 directly. So when I plug in 0 directly, I get 1. Okay, so this would be an example of a convergent integral, because I get a finite number. I get 1. Okay. All right. So that's the type 2 kind of improper integral. I guess the last thing to talk about here is the comparison test for improper integrals. We'll save that for the next video.